What if everything you know about the end of the universe is wrong? Picture this: a cosmos that doesn't fade into darkness, but ignites anew, reborn from its own remnants like a celestial phoenix. This isn't science fiction. It's one of the most profound mysteries scientists and philosophers have grappled with for centuries: the idea that our universe might not have a final ending at all. Instead, it could be part of an endless cycle of destruction and rebirth, a cosmic dance stretching across eternity. And today, we're diving deep into 29 astonishing theories that explore how this cosmic resurrection might actually happen. From the ancient Hindu concept of Brahman's breath to modern quantum physics, humanity has always been captivated by the idea of cyclical time. Think about it: every culture has its own version of the phoenix myth, a symbol of renewal rising from ashes. But what if that myth isn't just a story? What if it's a clue hidden in plain sight, hinting at the universe's true nature? Some of the brightest minds in cosmology now believe that the Big Bang might not have been the beginning but merely a reboot, a moment when an older universe collapsed and reshaped itself into the reality we know today. And if that's true, then the end of our universe might just be the start of something even grander. So how could this cosmic rebirth actually work? Could black holes hold the key, funneling matter into new dimensions? Or does the answer lie in the strange, shimmering fabric of quantum mechanics, where particles blink in and out of existence, hinting at a deeper, hidden order? Over the next 29 theories, we'll explore mind-bending possibilities from parallel universes colliding to dark energy, unraveling space-time only for it to stitch itself back together. This isn't just about the fate of stars and galaxies. It's about the very nature of reality itself. And by the end of this journey, you might never look at the night sky the same way again. So let's begin, because the story of the universe's rebirth is waiting to be told. The Big Crunch theory paints a dramatic picture of the universe's fate, one where the same force that holds us to the ground could one day pull every galaxy, every star, and even the fabric of reality itself back into a single, unimaginably dense point. Imagine the cosmos reversing its own expansion, like a movie played in rewind, until all matter and energy are compressed into a searing hot singularity. It's a concept that feels almost mythological, echoing ancient stories of worlds consumed by fire only to rise again. But here's where it gets even more fascinating. What if that catastrophic collapse isn't an end, but a cosmic reset button? Some theorists propose that the conditions inside a Big Crunch, where temperatures and pressures reach infinity, could mirror those of the Big Bang itself. In that moment of extreme compression, the laws of physics as we know them might break down, creating a kind of quantum spark that ignites a new universe. Think of it like a phoenix, but instead of feathers and flame, its entire galaxies being reborn from the ashes of the old. This cyclical model, often called the Big Bounce, suggests that our universe could be just one in an endless series, each expansion eventually giving way to contraction, each collapse birthing a new beginning. But how plausible is this idea? For decades, the Big Crunch seemed inevitable until astronomers discovered dark energy, the mysterious force accelerating the universe's expansion. Now, the question isn't just whether gravity could win the cosmic tug of war, but whether the conditions of a crunch could even produce a rebound. Some quantum gravity models suggest that at those unimaginable densities, space-time might behave in ways we can't yet predict, warping into a bridge between one universe and the next. Others argue that without a precise balance of energy and matter, a crunch might simply fizzle into eternal darkness, What's striking about this theory isn't just the science, it's the profound symmetry it offers. A universe that ends where it began, a cycle as timeless as the seasons, where every finale carries the seeds of a new dawn. Whether or not the Big Crunch proves to be our fate, it reminds us that the cosmos has a way of defying our simplest expectations, turning endings into beginnings in ways we're only beginning to understand. The Big Bounce hypothesis takes the drama of the Big Crunch and adds an exhilarating twist. What if the universe doesn't just collapse, but springs back like a cosmic rubber band? Picture a universe so dense and hot at the moment of collapse that the very laws of physics twist into something unrecognizable. At that critical point, quantum gravity, a theory still being pieced together by scientists, might step in, acting like an invisible trampoline that propels everything outward again. Instead of a definitive end, you'd have a rebirth, a new Big Bang forged from the remnants of the old. It's not just destruction, it's transformation on the grandest scale imaginable. What makes this idea so compelling is how it redefines time itself. If the Big Bounce is real, then our universe isn't a one-time event but a single heartbeat in an eternal cosmic rhythm. Each cycle could last trillions of years, with galaxies forming, stars burning out, and black holes merging, only for it all to reset and begin anew. Some theorists even suggest that subtle fingerprints of past universes might linger in the cosmic microwave background, the faint afterglow of the Big Bang. Imagine uncovering those echoes like finding pages from an older universe's diary hidden in the fabric of our own. But how would a bounce actually work? When matter and energy compress to near infinite density, quantum effects could create a repulsive force strong enough to counteract gravity's pull. Think of it like squeezing a spring. Push hard enough and it snaps back with stored energy. In this case, the spring is spacetime itself, rebounding with enough force to birth an entirely new cosmos. Recent computer simulations show that under certain conditions, a bouncing universe could preserve mathematical relationships from its predecessor, hinting that some fundamental laws might carry over from one cycle to the next. Yet mysteries remain. Would each new universe be a perfect replica of the last, or would slight variations creep in, creating infinite versions of reality? And if traces of past cycles exist, how could we detect them? Some scientists are scouring the cosmic microwave background for unusual patterns, anomalies that might be scars from a collision with a previous universe. Others are probing the behavior of space-time at the smallest scales, searching for clues about how quantum gravity could make a bounce possible. The beauty of the Big Bounce isn't just in its audacity, it's in the way it turns cosmic doom into a story of renewal. Even if our universe someday contracts to a single searing point, it might not be the end. Instead, it could be the prelude to another chapter in an epic that has no final page. And if that's true, then every star, every planet, every atom in existence is part of something far older and more resilient than we ever imagined. Conformal cyclic cosmology turns our understanding of time and space inside out, literally. Imagine a universe so stretched thin by expansion that all matter has evaporated, black holes have decayed, and even light struggles to cross the void. In this frozen, empty state, something extraordinary happens. The distinction between beginning and end blurs into mathematical symmetry. Nobel Prize winner Roger Penrose proposes that this distant future isn't an end at all, but a transformation. Through a process called conformal rescaling, the infinite vastness of a dead universe becomes mathematically identical to the infinitesimal singularity of a Big Bang. It's as if the cosmos folds in on itself, not through collapse, but through a rewriting of the rules. What's truly mind-bending is Penrose's claim that we might already have evidence of this cycle. He points to mysterious Hawking points, unusual hotspots in the cosmic microwave background as potential echoes of black holes from a universe that existed before ours. These points, named after Stephen Hawking, would be the last remnants of supermassive black holes that evaporated over eons, releasing bursts of energy that left faint imprints on the newborn cosmos. If real, they'd be like cosmic fingerprints, proof that our universe is just one page in an infinite book. But how could a cold, lifeless void become the seed of a new fiery beginning? The key lies in the geometry of spacetime itself. In the far future, when particles are spread so thin they barely interact, the universe becomes scale invariant. It looks the same whether you zoom in or out. At that point, the endless stretch of empty space can be mathematically rescaled to match the conditions of a singularity. It's not that the universe contracts. Instead, its very meaning of size and duration resets. Time loses its grip, and what was once the distant future becomes, in a twist of physics, the next Big Bang. Critics argue that conformal rescaling requires conditions so precise they border on the miraculous. Yet Penrose's ideas challenge us to rethink not just the universe's fate, but its identity. If he's right, then every galaxy, every star, every atom is part of a sequence stretching infinitely backward and forward, a cosmic Ouroboros where each ending is a beginning in disguise. And those enigmatic Hawking points, they could be our first glimpse into a past we never knew existed, hidden in plain sight within the afterglow of creation itself. The audacity of this theory lies in its elegance. No collapse, no bounce, just a quiet rearrangement of the cosmic ledger. It suggests that the universe doesn't die with a bang or a whimper, but with a whisper, one that somehow carries the blueprint for everything to start again. Whether or not Penrose's vision holds, it forces us to confront a staggering possibility, that beginnings and endings might just be illusions, artifacts of our limited perspective in an endless dance of existence. Eternal inflation rewrites the cosmic rulebook entirely instead of a single universe living and dying. Picture an endlessly churning multiverse where new realities bubble into existence like foam on an infinite ocean. In this mind-bending scenario, our entire cosmos might just be one accidental pocket of stability in a sea of runaway expansion. Here's how it works. Space itself is constantly stretching faster than light, a process called inflation. But occasionally a tiny patch slows down, cools, and crystallizes into a universe like ours. That moment of pause, that's your Big Bang, not the beginning of everything, but the quiet birth of one bubble among countless others. What's staggering about this idea isn't just the scale, it's the randomness. Each bubble universe could emerge with wildly different rules. Some might have gravity 1,000,000 times stronger, or atoms that refuse to stick together. Others could flicker out instantly, collapsing before they even form a single star. Our universe, with its just right physics for life, might be a cosmic lottery winner in a sea of failed experiments. And while we're here wondering about rebirth, the larger multiverse doesn't even notice. It keeps inflating eternally, spawning new bubbles with no end in sight. But here's where it gets even stranger. Some theorists suggest that bubble universes aren't entirely isolated. Under the right conditions, a collision between two bubbles could leave scars in the cosmic microwave background, like bruises from a hit and run with another reality. Astronomers have actually searched for these patterns, hunting for odd ripples in the afterglow of the Big Bang that might betray a long-ago crash with a neighboring universe. Imagine proving not just that other universes exist, but that we've literally bumped into them. Yet eternal inflation raises a haunting question. If our universe is just one accidental bubble, could its demise, whether by heat, death, or collapse, simply feed back into the infinite froth? Picture a black hole in our universe tunneling through space-time to become the seed of a new bubble elsewhere. Even as one reality fades, the multiverse keeps churning, turning endings into beginnings on a scale so vast it redefines the word eternity. This isn't just about cosmic recycling, it's about reimagining our place in existence. If eternal inflation is real, then every galaxy, every planet, every one of us is here because of a quantum fluctuation in an unthinkably vast arena we'll never see. And somewhere out there, in the endless expanse of inflating space, another bubble might be slowing down right now, cooling into a new universe with its own version of this very question. Black holes have long been the universe's ultimate enigmas, cosmic traps where gravity wins so decisively that not even light can escape. But what if these monstrous voids aren't just destroyers? What if each one is a cosmic womb, cradling an entirely new universe within its inky depths? This radical idea, known as black hole cosmology, flips our understanding of singularities on its head. Instead of being dead ends, black holes could be bridges, tunnels where matter and energy are crushed so violently that they trigger a new Big Bang, birthing a fresh space-time bubble inside the very heart of darkness. Think of it like a Russian nesting doll, but on a scale beyond comprehension. Our universe, with its billions of galaxies, might itself be the interior of a black hole from some grander, older cosmos. And every black hole we've detected, from the stellar mass ones peppering our galaxy to the supermassive beasts at galactic centers, could be incubating their own fledgling realities right now, hidden behind event horizons we can never cross. The math behind this is as elegant as it is strange. When matter collapses into a singularity, the equations of general relativity break down, but some quantum gravity models suggest that the crushing pressure might not lead to oblivion. Instead, it could twist space-time so severely that it pinches off into a separate, self-contained universe with its own laws and dimensions. This idea isn't just speculative poetry, it's grounded in real physics. The late physicist Nikodem Poplawski proposed that the inward collapse of matter inside a black hole could rebound outward in another space-time frame, like a cosmic knot tied so tightly it forms a new loop. In this scenario, the Big Bang wasn't a unique event but a commonplace occurrence, happening endlessly across the multiverse wherever black holes form. Even stranger, this could explain why our universe appears so finely tuned for life. If each black hole spawns a universe with slightly tweaked physical constants, most might be inhospitable voids, but statistically, a few would land in the Goldilocks zone, allowing stars, planets, and eventually curious minds to ponder their origins. But how could we ever test such a mind-bending theory? Clues might lie in the spin of black holes. If our universe was born inside one, it could have inherited a subtle rotational preference, a cosmic handedness imprinted in the large-scale structure of galaxies. Some researchers are also hunting for anomalies in the cosmic microwave background, patterns that could hint at a parent universe's influence. And if black holes really are cosmic matryoshka dolls, then the fate of our own universe takes on a haunting duality. As black holes evaporate over eons via Hawking radiation, their child universes might be cut adrift, orphaned realities floating in a void we'll never see. The beauty of black hole cosmology isn't just in its audacity, but in how it redefines destruction as creation. Every time a star collapses or galaxies merge, it might not be an ending. It could be the first breath of a cosmos we'll never know. And if that's true, then the night sky isn't just a collection of distant lights. It's a gallery of potential universes, each waiting for its turn to unfold. Quantum mechanics has always thrived on the improbable particles appearing out of nowhere, electrons teleporting through barriers, entire atoms existing in two places at once. Now stretch that strangeness to cosmic proportions. What if the universe itself could pull off the ultimate quantum trick, not with a dramatic collapse or a fiery bounce, but with a silent, spontaneous leap, a resurrection born from the sheer stubbornness of probability? This is quantum resurrection, a theory so audacious it makes black holes look predictable. At the heart of this idea lies the quantum vacuum, a seething ocean of potential where particles flicker in and out of existence like sparks in the dark. Normally, these fluctuations are fleeting, vanishing almost as soon as they appear, but given enough time, and we're talking timescales so vast they dwarf the age of our universe, even the most unlikely event becomes inevitable. Picture a quantum tremor so vast it ripples through the entire fabric of space-time, tunneling the cosmos into a fresh configuration. No collapse, no crunch, just the universe hitting the cosmic equivalent of a reset button. The math behind this isn't pure fantasy. Quantum field theory allows for the possibility of vacuum decay, where a bubble of true vacuum forms and expands at light speed, rewriting the laws of physics as it goes. But resurrection takes it further. Instead of destruction, imagine a fluctuation so precise it rebuilds rather than erases, a cosmic roll of the dice that lands the universe back in a state resembling the Big Bang. Some models even suggest that the new universe could inherit quantum information from its predecessor, like a faint genetic code passed between cosmic generations. Critics argue that the odds of such an event are so vanishingly small they might as well be zero. But here's the twist: in an infinitely old universe, or one cycling through eternal inflation, impossible is just a matter of patience. Given an eternity, every configuration of matter and energy, no matter how unlikely, must eventually occur. That includes a universe spontaneously rebooting itself. It's the ultimate expression of the quantum mantra: if something isn't forbidden, it's mandatory. What's mesmerizing about this idea isn't just the physics, it's the philosophical weight. If quantum resurrection is possible, then heat death, the cold fade to black predicted by thermodynamics, might not be the end. Somewhere in the darkness, against all odds, a spark could ignite. Not because of gravity or dark energy, but because the universe, given enough time, refuses to stay silent. And if that's true, then even in the deepest void, there's always a chance for light to return. Holographic universe theory suggests something astonishing: that all the stars, galaxies, and even your own thoughts might just be an elaborate projection, like a cosmic mirage. Imagine our three-dimensional reality as nothing more than a hologram, its true blueprint encoded on a distant two-dimensional surface. This isn't science fiction. It's a serious hypothesis born from studying black holes, where physicists discovered something bizarre. The information swallowed by these cosmic voids doesn't vanish. Instead, it gets imprinted on their event horizons like data etched onto a celestial hard drive. Now, stretch that idea to the entire universe. If reality is fundamentally information, then cosmic death might not mean oblivion, just a transfer of data. Think of it like a computer crashing. When your screen freezes, the software might fail, but the underlying code remains intact. Reboot the system and everything reloads. In the holographic model, the universe could operate the same way. As our cosmos expands toward heat death, its information, every particle interaction, every quantum state might be preserved on some vast, lower-dimensional boundary. Then, when conditions are right, that data gets reprocessed, sparking a new Big Bang. It's not a rebirth of matter, but of meaning, as if the universe is translating its own history into a fresh iteration. This theory gains traction from black hole thermodynamics. When matter falls into a black hole, its information isn't destroyed. It's scrambled and stored on the event horizon's surface. Physicists call this the holographic principle, and it hints that the universe might conserve information in the same way. If true, then even as galaxies fade and black holes evaporate, the story of the cosmos, its laws, its structures, perhaps even the echoes of past civilizations, could survive, waiting to be rewritten into a new reality. But how would this cosmic reboot actually work? One possibility involves quantum entanglement, the strange phenomenon where particles remain connected across vast distances. Some theorists suggest that entangled networks could act as a backup system, preserving relationships between bits of information even as space-time itself unravels. Picture a universe where every atom is part of a vast, interconnected code. When one iteration ends, those entangled links might provide the scaffolding for the next. The implications are staggering. If holographic rebirth is real, then our universe could be one in an endless series, each one a slightly altered version of the last. Minor glitches in the code might explain why physical constants are so finely tuned for life. We could be living in a successful iteration after countless flawed drafts. And if information truly persists, then somewhere, somehow, the essence of all that ever existed might yet find a way to return. This isn't just about physics, it's about the nature of existence itself. Are we living in a cosmic simulation, a shadow cast by some deeper reality? The holographic principle doesn't answer those questions, but it twists them into something even more profound. If the universe can preserve and reboot its own code, then endings aren't final, they're just pauses in an infinite loop of reinvention. And if that's true, then every moment, from the birth of a star to the flicker of a thought, might be part of a story far bigger and stranger than we ever imagined. Dark energy is the universe's greatest paradox, an invisible force pushing galaxies apart faster and faster, yet it might also hold the secret to cosmic rebirth. Right now, it's stretching space-time like an infinite rubber band, but what if that's only half the story? Some theories suggest dark energy isn't constant. It could evolve, weaken, or even flip its own script. Imagine a future where this mysterious force suddenly shifts gears, trading acceleration for attraction. Instead of drifting apart, galaxies could reverse course, drawn back together by dark energy's altered grip. It's like a cosmic pendulum swinging from expansion to contraction, setting the stage for a dramatic collapse and potentially a new beginning. But there's another, even wilder possibility: phantom energy. Unlike ordinary dark energy, phantom energy grows stronger over time, stretching space-time so violently that it overcomes the very fabric holding reality together. Picture a universe where not just galaxies, but atoms, nuclei, and even space-time itself are ripped apart in a cataclysmic Big Rip. Yet from that chaos, quantum physics offers a glimmer of hope. In the seething energy left behind, fluctuations could spawn entirely new universes, cosmic phoenixes rising from the ashes of the old. It's as if the universe's death scream becomes the first cry of something new. The key to these scenarios lies in dark energy's elusive nature. We know it makes up about 68% of the universe's energy budget, but we don't know what it is. Is it a static property of space, or does it change like a cosmic weather system? Some models propose that dark energy could interact with dark matter, trading energy in ways that alter the fate of the cosmos. Others speculate it might be tied to quantum fields we haven't discovered yet, fields that could flip polarity under extreme conditions, turning repulsion into attraction. What's fascinating is how these theories reframe dark energy from a destroyer into a potential architect of renewal. Even in the most extreme scenarios like the Big Rip, the destruction isn't necessarily absolute. Quantum mechanics allows for tiny bubbles of false vacuum to tunnel into new states, birthing pocket universes with their own laws. Our entire cosmos might one day be reduced to a froth of quantum foam, but within that foam, new realities could flicker to life, each carrying a fragment of the physics that made our universe possible. The deeper we dig into dark energy's mysteries, the more it blurs the line between end and beginning. Whether it's a cosmic pendulum swing or an explosive rebirth from phantom energy's wreckage, one thing is clear. The force we thought was driving the universe toward eternal silence might also be the spark that lights the next fire. And if that's true, then the fate of everything from the largest galaxy to the smallest atom rests in the hands of a shadow we're only just beginning to see. Loop quantum gravity cyclic model offers a radical twist on cosmic rebirth, one where the universe doesn't just bounce, but rewrites the rules of space and time themselves. Picture spacetime not as a smooth, continuous fabric, but as a tapestry woven from countless tiny loops, each one a billion times smaller than an atom. These loops are the universe's fundamental building blocks, and when matter and energy compress to extreme densities, they don't collapse into a singularity. Instead, they stretch and twist like a cosmic spring, reaching a point where gravity's pull flips into a repulsive force. The result, a rebound so powerful it births a new universe, all without the infinite densities that plague classical theories. What sets this model apart is its elegance. In Einstein's general relativity, singularities are mathematical nightmares, points where equations break down and physics loses meaning. But loop quantum gravity sidesteps this entirely. Here, spacetime's granular structure acts like a safety net, preventing the universe from crushing itself into oblivion. Think of it like squeezing a foam mattress. No matter how hard you press, the foam's tiny cells prevent it from collapsing to zero volume. Similarly, those spacetime loops ensure the cosmos always has an escape hatch, a quantum pressure valve that triggers rebirth instead of ruin. The implications are staggering. If this model holds, then the Big Bang wasn't a one-time explosion from nothingness, it was the latest turn in an endless cycle. Each bounce could carry subtle traces of the universe that came before, encoded in the geometry of spacetime itself. Some theorists even speculate that gravitational waves, those ripples in the cosmic fabric, might hide faint echoes of pre-bounce events. Imagine detecting a whisper from a universe older than time, a cosmic fossil buried in the vibrations of merging black holes. But how does this quantum bounce actually unfold? As the universe contracts, its energy density skyrockets, but instead of reaching infinity, the loops of spacetime resist further compression. The closer everything gets, the stronger the repulsion grows, until the collapse reverses in a cosmic U-turn. This isn't just a theory, it's been simulated using loop quantum cosmology, a simplified version of the full model. The math shows a smooth transition, like a ball bouncing off an invisible trampoline, with no singularities or breakdowns in physics. Critics argue that the model still lacks experimental proof, but its mathematical consistency is tantalizing. Unlike string theories, extra dimensions, or multiverse hypotheses, loop quantum gravity's cyclic universe makes testable predictions. If primordial gravitational waves bear a specific polarization pattern, or if the cosmic microwave background shows unexpected asymmetries, it could hint at spacetime's looped structure, and by extension, the universe's cyclical nature. The beauty of this idea lies in its duality. It unifies the quantum and cosmic scales, suggesting that the same tiny loops governing atoms could also dictate the fate of galaxies. And if the universe truly cycles through endless rebirths, then every star, every planet, every conscious mind is part of a story with no true beginning or end, just an infinite dance of collapse and renewal, written in the language of spinning spacetime threads. Brain collision scenarios take string theory's abstract mathematics and turn it into a cosmic blockbuster, one where universes don't just exist, but crash into each other like titans in the dark. Imagine our entire reality as a three-dimensional sheet, or brane, adrift in a higher dimensional space we can't perceive. Now picture another brane, another universe, drifting closer until bang, they collide. The energy of that impact could ignite a new Big Bang, birthing a cosmos from the wreckage of the collision. It's not just a theory, it's a symphony of creation, with each crash of the symbols marking the birth of a new universe. What makes this idea so compelling is how it redefines the Big Bang. Instead of a singular, inexplicable event, it becomes part of a cycle, a cosmic heartbeat driven by the gravitational dance of branes. Some models, like the Echperotic universe scenario, suggest our own universe began this way. Before the hot, dense state we call the Big Bang, there might have been a cold, quiet moment where two branes touched, releasing energy so immense it sparked everything we know. And if branes can collide once, why not again? The universe's rebirth might not come from within, but from beyond, as unseen dimensions deliver the ultimate cosmic reset. But how could branes, objects we can't even see, trigger such colossal events? The answer lies in the hidden dimensions string theory proposes. In this framework, gravity isn't confined to our brain. It leaks into the higher dimensional bulk, tugging other branes closer over eons. When they finally meet, the kinetic energy converts into the searing heat of a new universe. Think of it like two sheets of cling film floating in water. When they stick together, the wrinkles and vibrations could represent the birth of galaxies, stars, and ultimately, us. The echoes of these collisions might still be detectable. Some physicists hunt for telltale patterns in the cosmic microwave background, anisotropies that could resemble the bruises left by a brane collision. Others speculate that gravitational waves, the ripples in spacetime from cataclysmic events, might carry faint traces of pre-Big Bang physics. If we could decode those signals, we might glimpse the universe that existed before ours, or even predict when the next collision could occur. Yet the most haunting question isn't about evidence, it's about scale. If branes collide cyclically, then our universe is just one page in an infinite library of realities, each with its own laws, its own history. Some might be barren wastelands, others could teem with life we can't fathom. And if the cycle continues, then every ending, every heat, death, or big crunch might just be the prelude to another collision, another beginning. The beauty of brane cosmology isn't just in its audacity, but in its humility. It suggests that everything we see, from the farthest galaxy to the smallest atom, might owe its existence to an event we'll never witness directly. Our universe could be the aftermath of a higher dimensional accident, a cosmic spark struck from the friction of unseen worlds. And if that's true, then the night sky isn't just a window to the stars, it's a reflection of dimensions we're only beginning to dream of. Vacuum decay sounds like the ultimate cosmic disaster, a single quantum hiccup rewriting reality itself. But hidden in that apocalyptic scenario might be the universe's strangest rebirth mechanism. Picture this: our cosmos isn't sitting in the most stable possible state, but teetering on a precarious ledge, like a marble balanced on the rim of a bowl. This false vacuum could at any moment tip into a lower energy state, a true vacuum, where the fundamental forces and particles we know cease to exist as we know them. The transition would spread at light speed, erasing everything in its path. Yet within that annihilation lies a twist. The new vacuum could birth an entirely different universe, with fresh physical laws and constants. It's not death, it's metamorphosis on a scale beyond comprehension. What makes this idea so chilling is how random it could be. Unlike the slow fade of heat death or the dramatic crunch of gravitational collapse, vacuum decay could strike without warning. A single quantum fluctuation in some distant corner of space might nucleate a bubble of true vacuum that expands relentlessly, rewriting physics as it goes. One moment you're sipping coffee, the next atoms no longer bond, light no longer travels, and the very concept of you becomes meaningless. But here's the paradox: that same bubble, filled with its new rules, could become the seed of a thriving universe unlike our own. The old laws, gravity's pull, electromagnetism's spark, might be replaced by forces we can't even name, crafting realities where black holes form in seconds or stars burn in colors beyond our visible spectrum. The mathematics behind this isn't speculative fantasy. Quantum field theory allows for such phase transitions, and experiments like those at the Large Hadron Collider subtly probe the stability of the Higgs field, the very scaffolding of particle mass. If the Higgs exists in a false vacuum, as some models suggest, then our universe is fundamentally unstable, a temporary edifice waiting to collapse into something more permanent. The odds might be astronomically low, like rolling a billion dice and having them all land on one, but given infinite time, even the rarest events become inevitable. Yet there's a haunting beauty to this fragility. If vacuum decay is possible, then our universe isn't just one possible reality, but one fragile iteration in an infinite tapestry. Other bubbles of true vacuum might already exist out there, each a self-contained cosmos with its own unique physics. Some could be sterile voids, others might harbor life so alien we'd fail to recognize it. And if our bubble pops, the cascade could trigger new bubbles elsewhere, like a cosmic game of dominoes where each fall creates a new world, the eerie takeaway. We might never see it coming. Unlike a dying star or a colliding galaxy, vacuum decay offers no spectacle, no warning flares, just an instant, silent rewrite. But in that erasure lies a cryptic hope. Even as one universe winks out, another begins, carrying forward the unbroken thread of existence in forms we can't yet imagine. Our reality could be both temporary and eternal, a single note in an endless symphony of cosmic reinvention. Time's arrow seems absolute. We remember the past but not the future. Eggs crack but never uncrack. Stars burn out but don't reignite. Yet what if this forward march is just an illusion, a local quirk in a cosmos where time is fundamentally circular? Ancient Hindu texts describe the universe breathing in and out over epochs called kalpas, each lasting billions of years, while the Mayans envisioned time as a series of nested cycles. But it's not just mythology. Modern physics toys with the same idea through closed time-like curves, paths in spacetime so warped by gravity that they loop back on themselves. If time isn't a straight line but a Möbius strip, then the universe's death might not be an end at all, just a return ticket to its own birth. Einstein's equations allow for such loops under extreme conditions, like near a rotating black hole or in a universe dense enough to twist spacetime into a knot. Picture a cosmic record player where the needle, instead of reaching the end of the groove, slides seamlessly back to the starting note. In this scenario, the Big Bang isn't a singular origin. It's the moment the universe completes its cycle, recycling everything from galaxies to quantum fluctuations into a fresh iteration. Even entropy, the measure of disorder that gives time its apparent direction, could reset in each cycle, like shuffling a deck of cards back to perfect order. The implications are dizzying. If time is cyclical, then every event, every supernova, every civilization, every thought has happened before and will happen again endlessly. This isn't just déjà vu on a cosmic scale. It's the universe trapped in an eternal echo. Some interpretations of quantum mechanics even suggest that particles remember their past loops, subtly influencing their behavior in ways we might one day detect. Imagine finding a pattern in the cosmic microwave background that repeats like a fractal, or a statistical anomaly in particle collisions that hints at a universe stuck in replay. Yet the most haunting question isn't about physics, it's about meaning. If time loops, are we destined to make the same choices forever? Or does each cycle introduce tiny variations, like a cosmic jazz improvisation on an infinite theme? The answer might lie in the fine print of quantum gravity, where the rules of the very small could dictate whether history repeats exactly or with creative license. Either way, the idea reshapes our place in existence. We're not just passengers in a universe moving toward some final state. We're participants in a story with no last page, where every ending is a beginning in disguise. The beauty of cyclical time isn't just its symmetry, but its defiance of oblivion. Even if the stars fade and black holes evaporate, the universe might not be marching toward silence. It could be whispering to itself in an endless conversation across eternity. And if that's true, then every moment from the birth of a galaxy to the blink of an eye is both unique and eternal, a note in a song that never truly ends. The Anthropic principle turns the mystery of our universe's fine-tuning into something deeply personal. Why does reality seem tailor-made for life? The answer might lie in an endless cycle of cosmic trial and error. Imagine a multiverse where countless universes flicker in and out of existence, each with random physical constants. Most would be stillborn, collapsing instantly or stretching into barren voids. But occasionally, by sheer chance, one hits the jackpot. Gravity weak enough to let stars form, nuclear forces precise enough to forge carbon, and dark energy balanced to allow galaxies to flourish. That rare universe, by virtue of its hospitable laws, becomes the stage for observers like us to ponder its existence. It's not that the cosmos was designed for life, it's that life can only arise in the universes capable of sustaining it. This idea, known as the selection effect, reshapes how we think about cosmic rebirth. If universes recycle endlessly, then each iteration could be a roll of the dice with slight variations in fundamental constants. Over enough cycles, the odds tilt toward configurations that permit complexity and eventually consciousness. Think of it like a vast cosmic laboratory where failed experiments vanish without a trace, while successful ones leave behind witnesses to marvel at their luck. Even the tiniest tweak to gravity or the strong nuclear force would render stars lifeless or atoms unstable. The fact that we're here means our universe's recipe passed an unimaginably rigorous test, one that might have taken infinite tries to get right. But here's where it gets even stranger. Some theories suggest that black holes or vacuum decay could spawn new universes with slightly tweaked physics, like cosmic offspring inheriting mutated genes. If life-friendly constants increase the odds of producing more black holes, as they seem to in our universe, then over eons, the multiverse could evolve toward habitable conditions. Not through intent, but through a form of cosmological natural selection. It's as if the universe itself is learning, refining its parameters with each rebirth to maximize the potential for complexity. Critics argue this reasoning feels circular. We exist, therefore the universe must allow existence. Yet the fine-tuning is hard to ignore. Change the cosmological constant by 1 part in 100 million, and galaxies never form. Adjust the quark masses by a hair, and protons disintegrate. The precision is so exact it begs for an explanation beyond coincidence. Whether the answer lies in an infinite multiverse, a self-correcting cycle of rebirth, or something even more profound, one thing is clear. Our presence here is either a statistical miracle or evidence of a cosmos far older and more intricate than we've dared to imagine. The haunting beauty of this idea isn't just in its science, but in its poetry. If true, we're not just passengers in a random universe, we're the echoes of countless failed realities, the lucky winners of a cosmic lottery that's been running since eternity began. And if the cycle continues, future universes might owe their existence to the same relentless tinkering that made ours possible. So when you look up at the stars, you're not just seeing light, you're reading a message from the void, written in the only language the cosmos understands: trial, error, and time. Entropy seems like the universe's ultimate fate, a slow, inevitable slide into disorder where stars burn out, black holes evaporate, and even atoms themselves decay into a featureless sea of particles. This bleak scenario, known as heat death, is baked into the second law of thermodynamics. Entropy, the measure of chaos in a system, always rises. But what if maximum entropy isn't the final word? What if the universe, in its quietest, most desolate state, still holds the seeds of its own resurrection? Take quantum fluctuations, those tiny, unpredictable bursts of energy that pop in and out of existence even in a vacuum. In a universe stretched thin by endless expansion, these fluctuations might be the last flickers of activity, but they could also be the first sparks of something new. Given enough time, a rare but inevitable quantum event could tunnel through the energy barrier of maximum entropy, birthing a fresh patch of space-time with lower entropy. It's like finding a single unshuffled card in a well-worn deck, statistically unlikely, but given infinite time guaranteed. Suddenly, the void isn't so empty anymore. A new cosmic cycle begins not with a bang, but with a whisper. Black holes offer another twist in the tale. As they evaporate via Hawking radiation, they don't just vanish, they release energy back into the cosmos. In the far future, when all else is dark, these dying black holes could be the last furnaces in the cold, their radiation stirring the embers of a dead universe. Some models suggest that this energy might not dissipate entirely. Instead, it could accumulate in quantum loops or space-time defects, creating regions of lower entropy where matter and energy begin to clump anew. Picture a forest after a wildfire. The ground seems barren, but beneath the ashes, seeds wait for the right conditions to sprout. Then there's the cyclical entropy model. If the universe rebounds, whether through a big bounce, brane collision, or some other mechanism, entropy might not carry over from one cycle to the next. Instead, the rebirth process could reset the cosmic ledger, like reshuffling that deck of cards back into perfect order. This isn't a violation of thermodynamics. It's a cosmic loophole where the laws themselves are part of a larger cyclical framework. Ancient Hindu cosmology envisioned this as the breath of Brahman. The universe exhales into chaos, then inhales back into order endlessly. Modern physics, in its own way, is flirting with the same idea. What's mesmerizing about these theories isn't just their audacity, it's how they reframe decay as potential. Even in the darkest, most disordered state, the universe might harbor hidden rhythms, patterns that defy our linear intuition. Heat death could be less of a finale and more of an intermission, a hushed pause before the next act begins. And if that's true, then entropy isn't the end of the story. It's just the turning of a page we can't yet read. White holes are one of the universe's most tantalizing what-ifs, theoretical cosmic geysers where matter and energy erupt outward instead of vanishing into darkness. If black holes are nature's ultimate drains, white holes would be their gushing counterparts, defying gravity's pull by ejecting everything they contain. The math of general relativity allows for such objects, though we've never observed one. Yet their potential role in cosmic rebirth is staggering. Picture a black hole in some distant universe, aging over eons until it evaporates via Hawking radiation. What if that evaporation isn't an end, but a transformation? Some models suggest the dying black hole's singularity could rebound as a white hole, spewing its contents, perhaps even an entire new universe, into existence like a cosmic phoenix rising from its own ashes. This idea turns the Big Bang into something even more profound, not a spontaneous eruption from nothingness, but the explosive output of a white hole born from a black hole's demise. In this scenario, our universe might be the other side of a collapse that happened elsewhere, its laws and constants shaped by the physics of its parent cosmos. Think of it like a seed pod bursting open, the dense, hidden core of one reality becoming the fertile ground for another. The equations hint that such a transition could avoid the infinite densities of a singularity, offering a smoother bridge between universes than traditional bounce or cyclic models. Yet white holes come with puzzles. Why don't we see them? If they exist, their radiant energy should make them visible across the cosmos. One possibility is that white holes are inherently short-lived, flashing into existence only long enough to birth a new spacetime before vanishing. Another is that what we perceive as the Big Bang was our lone encounter with a white hole, an event so monumental it set every galaxy, every star in motion. Some theorists even propose that dark matter could be the faint afterglow of primordial white holes, their remnants woven into the fabric of our universe like cosmic dust. The most radical version of this idea comes from loop quantum gravity, where black holes never form singularities at all. Instead, their crushing gravity reaches a point where spacetime's quantum structure resists further collapse, triggering a reversal. The black hole becomes a white hole, but with a twist. The transition might take billions of years from an outside perspective, while appearing instantaneous to anything inside. To an observer in the parent universe, the black hole seems to evaporate slowly, but to whatever's trapped within, the rebirth is immediate, a blink between the old cosmos's end and the new one's fiery dawn. Whether white holes are real or not, their theoretical existence challenges our notions of beginnings and endings. If matter and energy can cycle through these cosmic airlocks, then universes might not be isolated accidents but linked chapters in an epic too vast to comprehend. And if that's true, then somewhere out there, in the depths of a black hole we'll never see, another reality might already be taking its first breath. Simulated universe resurrection flips the script on cosmic rebirth entirely. What if the universe isn't just governed by physics, but by lines of code? Imagine reality as an unfathomably advanced simulation, where the laws of nature are actually parameters set by some higher dimensional programmer. In this scenario, the end of our universe could be as mundane as someone hitting the reset button, tweaking a few variables and launching a fresh iteration. It's not just a sci-fi trope. Serious thinkers like Nick Bostrom and Elon Musk have entertained the idea that the odds we're living in base reality are vanishingly small. If they're right, then cosmic death might not be about collapsing singularities or bouncing branes, but about server maintenance. Think of it like a video game. When you power off your console, the world inside doesn't vanish, it's preserved in code, ready to reload. Now scale that up to a universe-sized simulation. An advanced civilization, perhaps billions of years ahead of us, might run countless iterations of cosmic history, experimenting with different gravity strengths, dark energy values, or even entirely new particle types. Our universe's eerie fine-tuning for life could simply be one successful run among countless failures, a configuration that finally produced conscious observers. And if the simulation glitches or reaches some predetermined endpoint, no problem. The architects could reboot with a patch, adjusting the rules to see what emerges next. This idea blurs the boundaries between physics and computer science. the quantum weirdness we observe particles existing in multiple states until measured. Entanglement acting like cosmic instant messaging could be processing optimizations in the simulation's code. Even the speed of light might just be a hardware limitation, a render rate preventing the system from overloading. And if the simulators are running multiple universes simultaneously, they might conserve resources by reusing assets, which could explain eerie parallels between seemingly unrelated phenomena. But here's the twist: if our universe is a simulation, its rebirth might not even require a full shutdown. Advanced civilizations could implement save states, preserving the data of one iteration to seed the next. Imagine a future where humanity develops the tech to create nested simulations. Our own universe could be a descendant of an earlier run, its parameters inherited like genetic traits. Over eons, these simulated realities might evolve, with each iteration refining the rules to produce more complexity, more consciousness, or some other unfathomable goal. The implications are as humbling as they are thrilling. If we're in a simulation, then the cosmos isn't just indifferent, it's experimental. Every supernova, every galaxy, every thought could be part of a grand data set, analyzed by entities we'll never perceive. And if the program resets, we might not even notice. One moment the stars fade to black, the next they flicker back on, their light obeying slightly different rules. The universe wouldn't die, it would just reload. Whether this theory feels like a revelation or a rabbit hole, it forces us to confront the deepest question of all. If reality is code, then who or what is the programmer? And more importantly, are they running out of storage space? Plato's ancient vision of a higher reality where our world is just a flickering shadow cast by perfect, eternal forms might hold the key to cosmic rebirth. Imagine a realm where circles are flawlessly round, where justice exists as an ideal untouched by human frailty, and where every object we see is merely a dim reflection of its truest self. Now take that idea and scale it up to the universe itself. What if the stars, galaxies, and even space-time are just imperfect copies of something far more profound? Modern thinkers like physicist Max Tegmark take this further, proposing that mathematics isn't just a tool to describe reality, it is reality. In this view, the cosmos we inhabit might be nothing more than a temporary projection of timeless, unchanging mathematical truth. This raises a breathtaking possibility. The death of our universe could simply be the fading of one particular manifestation, while the underlying mathematical structures persist, ready to generate new physical realities. Think of it like a symphony. The notes fade, but the composition remains, waiting for another orchestra to bring it to life. If mathematical laws are the eternal score, then cosmic rebirth isn't about matter collapsing and reforming, but about the same equations manifesting anew in fresh configurations. A black hole's singularity, the quantum foam of empty space, even the mysterious fine-tuning of physical constants, all of these could be echoes of a deeper mathematical order, momentarily wearing the mask of physics. But how would this actually work? Some theories suggest that certain mathematical structures naturally give rise to self-contained universes under the right conditions. For example, the equations governing quantum fields might resolve into stable configurations over and over, like a kaleidoscope cycling through its patterns. Each time, the universe would look different particles, different forces, but the core relationships, the symmetries and ratios would remain immutable. It's as if existence is a movie and mathematics is the film reel, capable of playing an infinite number of slightly varied versions of the same story. The implications are staggering. If the Platonic view is correct, then the Big Bang wasn't the beginning of everything, just the latest instantiation of a truth that has always been. And if the universe ends in heat death or a big crunch, it wouldn't mean the end of reality, only the closing of one chapter. The mathematical bedrock would endure, and somewhere, somehow, another universe could emerge, its laws dictated by the same eternal forms. We might even be living in one of countless iterations, each one a slightly imperfect rendering of the perfect template. The beauty of this idea lies in its duality. It's both ancient and cutting-edge, blending philosophy with theoretical physics. Whether Plato's forms are real or just a metaphor, they challenge us to ask, is the cosmos we see the ultimate reality, or just a shadow on the wall of a far grander cave? And if it's the latter, then every ending is just an intermission, a pause before the numbers rearrange themselves and the universe begins again. Chaotic inflation turns the birth of our universe from a singular event into an endless cosmic chain reaction, one where reality is constantly hatching new realities in a frenzy of quantum spontaneity. Picture the early universe not as a calm, orderly expansion, but as a seething quantum foam where random fluctuations spawn pockets of runaway inflation. Each of these bubbles pinches off into its own self-contained cosmos, with its own unique physics, while the larger multiverse continues expanding chaotically around it. Our universe, with its just right conditions for life, might be nothing more than a lucky accident in this infinite cosmic lottery. What makes chaotic inflation so mesmerizing is its sheer unpredictability. Unlike traditional inflation models, where the universe expands smoothly like a balloon inflating, this version is messy and anarchic. Quantum jitters constantly tweak the energy fields driving inflation, creating regions where expansion slows enough for matter to form. These become universes while other regions keep stretching exponentially. It's like a boiling pot where bubbles of steam form and rise, except each bubble is an entire reality, and the pot never stops boiling. Some universes might last mere microseconds before collapsing, others could endure for trillions of years. Ours happens to be in the Goldilocks zone, where inflation paused just long enough for galaxies to coalesce, but not so long that everything was diluted into nothingness. The implications are staggering. If chaotic inflation is real, then the multiverse isn't just a collection of parallel worlds, it's a living, breathing entity, endlessly giving birth to new cosmoses with every quantum flicker. Each bubble universe could have wildly different constants. Gravity might be weaker in one, electromagnetism stronger in another. Some might be crammed with black holes, others could be vast, empty deserts where atoms never even form. And because inflation never stops, the process is eternal, with no beginning or end, just an infinite fractal of cosmic possibilities. But how could we ever prove such a theory? Some physicists hunt for evidence in the cosmic microwave background, the afterglow of the Big Bang. If our universe collided with another bubble during inflation, the crash could have left faint imprints, like bruises on space-time visible in the microwave patterns. Others study the distribution of galaxies, searching for anomalies that might betray our universe's turbulent birth. Even if direct proof remains elusive, the math behind chaotic inflation is compelling, offering a way to explain the universe's fine-tuning without invoking divine intervention or sheer luck. Life exists here because in an infinite multiverse, every possible configuration must arise somewhere. The beauty of this idea isn't just its scale, it's the way it redefines existence itself. Universes aren't precious or rare, they're as commonplace as waves in an ocean, each rising and falling in an endless cycle. And if the multiverse keeps churning out new realities forever, then the death of our cosmos isn't a tragedy, it's just one more bubble popping in an infinite sea of creation. Somewhere, right now, another universe might be flickering to life, its own version of this story just beginning to unfold. The Echperotic universe model turns the traditional Big Bang narrative on its head. Instead of a fiery explosion from nothingness, picture a slow, deliberate cosmic collision between two immense membranes drifting through higher dimensional space. These membranes, or branes as string theorists call them, could be vast, sheet-like structures existing in dimensions beyond our perception. When they finally meet, the impact doesn't shatter or destroy. It transforms, releasing energy so immense it spawns an entirely new universe. This isn't chaos, it's more like a carefully choreographed dance, where the universe's birth isn't a singular, violent event, but a rhythmic exchange of energy across dimensions we can't even see. What makes this idea so compelling is how it sidesteps the Big Bang's biggest puzzle, the singularity. In classical cosmology, the universe erupts from an infinitely dense, infinitely hot point where physics breaks down entirely. But the Echperotic model offers an elegant workaround. The collision between branes transfers kinetic energy into the fabric of space-time itself, heating it to extreme temperatures without requiring a singularity's impossible conditions. Think of it like clapping your hands together. The sound isn't born from a single point inside your palms, but from the interaction between them. Similarly, our universe's birth might not stem from a mysterious zero point, but from the meeting of two colossal structures in a hidden dimensional arena. The cyclical nature of this model is where things get truly mesmerizing. If branes can collide once, why not again and again? Imagine these higher dimensional sheets drifting apart after their initial impact, only to be drawn back together over eons by unseen forces, perhaps gravity leaking into the bulk dimensions between them. Each collision resets the cosmic clock, igniting a new universe with its own laws, constants, and potential for life. It's not a one-time creation story. It's an endless symphony of cosmic renewal, where every crescendo marks the dawn of another reality. But how would such a collision actually unfold? Unlike the Big Bang's instantaneous explosion, the Echperotic scenario might begin in near total darkness. The pre-collision universe could have been cold, empty, and eerily quiet, a far cry from the searing plasma we associate with cosmic origins. Then, as the branes inch closer, quantum fluctuations stretch and warp, seeding the irregularities that will later become galaxies. By the time the branes finally touch, the universe is already primed for structure, avoiding the need for a separate inflation period to explain why matter isn't perfectly evenly distributed. It's as if the cosmos arrives with its blueprint pre-etched, its destiny written into the very act of creation. Critics argue that the Echperotic model relies on speculative physics. After all, we have no direct evidence of higher dimensions or colliding branes. Yet it offers solutions to problems that plague traditional cosmology, like the horizon problem. Why distant regions of the universe look so similar despite never being in contact. In the Echperotic scenario, those regions were once part of the same smooth brane, their uniformity baked in long before the collision. Supporters also point to potential fingerprints in the cosmic microwave background, subtle patterns that could betray a pre-Big Bang phase of contraction rather than expansion. Finding those patterns wouldn't just validate the theory, it'd rewrite our entire understanding of time's arrow. The beauty of the Echperotic universe isn't just in its mechanics, but in its poetry. It suggests that existence isn't linear but cyclical, a series of cosmic seasons where each winter gives way to spring. Even the name, borrowed from the ancient Greek word for conflagration, hints at this duality, destruction and rebirth intertwined. Whether the model holds up to future tests or not, it challenges us to rethink the most basic questions. Was there ever a true beginning? Or are we just one verse in an endless hymn of collisions, each one echoing across dimensions we're only beginning to dream of? At the smallest scales imaginable, far tinier than an atom, beyond even the quarks and electrons that make up matter, the universe stops playing by the rules we know. Here, in the realm of the Planck length, gravity and quantum mechanics collide in a storm of uncertainty, where space-time itself frays into a bubbling quantum foam. Picture an ocean during a hurricane, but instead of waves, you've got fleeting bubbles of reality forming and popping in a chaotic dance. This isn't just theoretical poetry, it's where the fate of entire universes might be decided. In this froth of potentiality, the very fabric of existence becomes fluid. Tiny wormholes might tunnel between disconnected regions of space-time, while miniature universes blink into existence and vanish before they can stabilize. Most of these baby universes would collapse instantly, snuffed out by their own instability. But occasionally, through sheer statistical chance, one might latch onto the right conditions to expand, a cosmic lottery winner destined to become a full-fledged cosmos like ours. The equations of quantum gravity suggest that these fledgling realities wouldn't emerge from nothingness, but from the seething energy of the quantum vacuum, where empty space is anything but empty. What's staggering about this idea is how it redefines the Big Bang. Rather than a singular, inexplicable event, our universe's birth could have been one ripple in an endless quantum sea, a fluctuation that somehow stuck. Some models even propose that black holes, those cosmic traps where gravity runs rampant, might be gateways to this process. As matter crushes into a singularity, the extreme conditions could trigger a quantum tunneling effect, pinching off a new space-time bubble in the foam. It's as if every black hole is a cosmic seed carrying the potential for rebirth within its very destruction. The implications ripple outward. If quantum foam births universes, then ours might not be unique or special, just one iteration in an infinite ensemble. Each would have slightly different physical constants depending on how the quantum dice landed during its formation. Most would be sterile voids, but a rare few, through sheer chance, would have the perfect balance for stars, planets, and life. This isn't just about how universes begin. It's about why ours seems so finely tuned for complexity. The answer might be as simple as statistics. In an endless froth of possibilities, even the most unlikely outcomes must eventually occur. Yet the most haunting question isn't about origins, it's about endings. If universes can emerge from quantum foam, could our own fate be to dissolve back into it? Imagine a distant future where space-time, stretched thin by dark energy, fractures into its fundamental components. The universe wouldn't end with a bang or a whimper, but with a quiet return to the foam, its energy recycled into the next cosmic fluctuation. In this view, death and rebirth aren't separate events, but two sides of the same quantum coin, eternally flipping in the dark. The beauty of quantum gravity's rebirth mechanism lies in its humility. It doesn't require higher dimensions, colliding branes, or simulated realities, just the raw, untamed physics of the very small, operating on scales we can barely fathom. And if this theory holds, then every atom in your body, every star in the sky, is here because somewhere, somehow, the quantum foam once bubbled in just the right way. Not with purpose, but with possibility, a reminder that even in the void, creation never truly stops. Cosmic consciousness theories push the boundaries of physics into the realm of the metaphysical. What if the universe doesn't just exist, but thinks? At the heart of this radical idea is a simple but staggering question. Does reality require observers to give it meaning? Quantum mechanics already hints at observer-dependence. Particles exist in probability waves until measured, collapsing into definite states only when observed. Scale that up to cosmic proportions and you're left with a spine-tingling possibility. The universe might not just contain consciousness, it could depend on it. Take the participatory anthropic principle, a twist on the classic idea that the universe is fine-tuned for life. This version goes further, suggesting that conscious observers don't just passively benefit from cosmic conditions, they're necessary for reality to crystallize. Without minds to perceive it, the universe might remain a fog of quantum potential, never fully actualizing. In this view, the death of all observers, whether through heat death, vacuum decay, or some other cosmic catastrophe, could trigger a collapse of reality itself. But here's the kicker: that collapse might not be the end. Like a quantum fluctuation in the dark, a new universe could bubble into existence, complete with its own observers to breathe it into being. It's as if consciousness is the universe's way of ensuring its own survival, cycling through iterations until it finds one where life can persist. This isn't just philosophical speculation. Some interpretations of quantum theory, like von Neumann-Wigner consciousness causes collapse, argue that observation isn't just a measurement, it's a creative act. If true, then the cosmos isn't a static stage but an interactive performance, with observers and observed locked in an endless dance. Imagine a future where the last sentient being in the universe closes their eyes, and in that final moment of observation, reality winks out only to reboot elsewhere, with new players stepping onto the cosmic stage. Critics dismiss this as idealism dressed in scientific jargon, pointing out that the universe existed for billions of years before life emerged. But proponents counter that time itself might be observer-dependent, a narrative thread woven by consciousness. Without observers, the past and future could dissolve into a timeless soup of possibilities, waiting for a mind to stitch them into coherence. Even the Big Bang might not be a fixed event but a retrospective one, its details shaped by the observers who later arose to ponder it. The most haunting implication: if consciousness truly underpins reality, then the universe isn't just allowing life, it's seeking it. Every black hole, every supernova, every random fluctuation could be part of a vast, unconscious experiment, testing configurations until it stumbles upon the right conditions for minds to emerge. And if those minds eventually perish, the cycle would continue: collapse, rebirth, and another chance for the cosmos to wake up and ask, "Am I alone?" Whether this is profound truth or poetic delusion, it forces us to confront our role in the cosmos, not as accidental passengers, but as potential co-authors of reality itself. What if the multiverse isn't just a chaotic scattering of random universes, but a cosmic ecosystem where only the fittest survive? This is the spine of multiverse natural selection, a theory that takes Darwin's principles and scales them up to reality itself. Imagine universes not as static, isolated bubbles, but as dynamic entities that compete, adapt, and even reproduce. In this grand arena, universes that generate more black holes or foster stable conditions might act like cosmic superspreaders, passing their traits to offspring universes through some form of cosmological inheritance. Our own universe, with its precise balance of forces allowing for galaxies, stars, and life, could be the product of eons of this invisible evolutionary pressure. Black holes play a starring role in this cosmic drama. If a universe's fitness is measured by its ability to create black holes gateways that might spawn new universes, then ours is a champion. Supermassive black holes anchor galaxies, while stellar mass ones dot the cosmic landscape like seeds. Some theories suggest that the extreme conditions inside a black hole's singularity could trigger the birth of a new spacetime bubble, complete with slightly tweaked physical constants. Universes that produce more black holes would, in turn, generate more offspring, spreading their genes across the multiverse. Over countless generations, this would favor universes capable of sustaining complexity long enough to forge these gravitational behemoths. It's survival of the most prolific, with spacetime itself as the battleground. But stability matters just as much as reproduction. A universe where atoms disintegrate instantly or gravity crushes stars before they form wouldn't last long enough to create black holes. Our cosmos strikes a delicate balance, strong enough gravity to pull matter into galaxies, but not so strong it collapses everything instantly. Nuclear force is precise enough to forge carbon, but not so weak they can't ignite stars. These Goldilocks conditions might not be accidental. They could be the result of multiverse-scale trial and error. Over infinite cycles, universes with inhospitable laws fizzled out, while those like ours persisted, their traits reinforced through cosmic generations. The implications ripple beyond physics into philosophy. If multiverse natural selection is real, then the fine-tuning of our universe isn't a miracle, it's inevitability. Just as Earth's biosphere evolved to fill every niche, the multiverse could be a jungle where only the most robust universes thrive. Even the arrow of time might be an adaptation. Universes where entropy increases predictably, allowing for the slow burn of stars and the rise of life, would outcompete those where chaos reigns. Critics argue this theory leans heavily on speculation, but its elegance is hard to ignore. It reframes the anthropic principle, the idea that we observe a life-friendly universe because we couldn't exist otherwise, as an active process rather than a passive observation. And if black holes truly are cosmic wombs, then the night sky isn't just a collection of distant light, it's a nursery for universes yet to be. Every galaxy's core, every colliding star system, could be part of a vast, unseen reproductive cycle. The most haunting question isn't whether this process exists, but what it's building toward. If universes evolve, could they one day reach some optimal form? Or is the multiverse an endless experiment, iterating toward no particular goal? Either way, the idea reshapes our place in existence. We're not just inhabitants of a universe, we're witnesses to its evolutionary journey, living proof that somewhere in the void, nature's oldest rule still holds: adapt, reproduce, endure. Quantum mechanics holds a sacred rule: information can never be destroyed. Not in a black hole's crushing depths, not in the heat death of the universe, never. This principle, known as unitarity, suggests that every particle interaction, every quantum state, every whisper of energy is eternally logged in the cosmic ledger. But here's the twist: if information is indestructible, could it also be reusable? Imagine the universe as a vast quantum hard drive, where the data encoding galaxies, stars, and even your thoughts isn't erased at the end of time, just reformatted. Some theories propose that this preserved information might be the raw material for cosmic rebirth, a blueprint waiting to be reloaded into a new iteration of reality. Take black holes, nature's most efficient shredders. For decades, physicists debated whether these gravitational monsters truly obliterate information, violating quantum mechanics' core tenets. Then came Hawking's breakthrough. Black holes slowly leak radiation, and that radiation carries traces of the information they've consumed. It's scrambled beyond recognition, like a book burned to ash, but the words, the fundamental quantum states, still exist in some form. Now stretch that idea to the universe's fate. If information survives a black hole's wrath, why not the heat death of everything? In the far future, when all stars have burned out and space-time has stretched into a thin, cold haze, quantum fluctuations might still preserve the universe's data, etched into the fabric of reality itself. This isn't just theoretical sleight of hand, it's a potential loophole in cosmic oblivion. If information persists, then the universe's death might be more like hibernation. Under the right conditions, that data could reconstruct itself, not as a perfect copy, but as a new configuration with echoes of the old. Picture a painter reusing a canvas. the underlying brushstrokes of a previous work still linger beneath fresh layers, subtly influencing the new image. Similarly, a reborn universe might inherit quantum correlations or symmetries from its predecessor, like a child inheriting a parent's genetic quirks. The mechanisms for this cosmic recycling are as wild as they are varied. One possibility involves quantum entanglement, the eerie link between particles that persists across any distance. As the universe expands, entangled networks could act as a backup system, preserving relationships between bits of information even as space-time frays. When conditions permit, those entangled states might rewrite themselves into a new cosmic epoch, like a dormant seed sprouting after a long winter. Another idea leans on holography, where the universe's entire information content is encoded on a two-dimensional boundary. In this view, heat death doesn't erase the data, it just archives it, waiting for the right trigger to reboot the simulation. Critics argue that information preservation doesn't guarantee reconstruction. A scrambled hard drive might contain all its original data, but without the right decryption key, it's effectively gibberish. Yet the mere possibility reshapes how we think about endings. If information is truly immortal, then the universe's story isn't bound by a single volume, it's an infinite series, with each installment written in the ink of quantum states. Whether through black hole evaporation, vacuum fluctuations, or some yet unknown process, the cosmos might have a way to repurpose its own history, turning finales into preludes in the dark. The beauty of this idea isn't just in its physics, but in its poetry. It suggests that existence is less like a candle snuffing out and more like a flame passed between generations, forever changing yet eternally persistent. And if that's true, then every atom, every photon, every fleeting thought is part of a chain stretching backward and forward through time, a cosmic heirloom waiting for its next incarnation. Time crystals sound like something ripped from a sci-fi novel, structures that pulse and cycle without any energy input, like a perpetual motion machine at the quantum level. But these aren't just theoretical oddities. They're real, experimentally confirmed phases of matter that defy our classical understanding of physics. Picture a snowflake that doesn't just sit there, but flips between two symmetrical configurations endlessly, like a ticking metronome frozen in time. Now stretch that idea to cosmic scales. What if space-time itself is a kind of time crystal, its very fabric oscillating between states on a time span so vast we mistake it for linear history? In this view, the universe's rebirth wouldn't be a cataclysmic event, just the next tick in an eternal cosmic clock. The key to this mind-bending possibility lies in symmetry breaking. Ordinary crystals like diamonds or salt break spatial symmetry. Their atoms arrange in repeating patterns, locking into a stable structure. Time crystals take this further by breaking time symmetry. They're stable, yet never settle into equilibrium, oscillating indefinitely even in their lowest energy state. If the universe operates on similar principles, then the Big Bang might not have been a one-time explosion, but the latest tick in a cycle stretching infinitely backward and forward. Instead of wondering how the universe could restart, we'd be forced to ask, could it ever stop cycling? Here's where the physics gets wild. In a time crystal universe, the arrow of time we experience, the unbroken march from past to future, could be an emergent illusion, a side effect of deeper cyclical processes. Think of it like watching a pendulum swing. From our limited perspective, it moves in one direction, then the other. But zoom out far enough, and you see it's just part of an endless rhythm. If space-time itself is oscillating, then heat death might not be the end, just the universe winding down to its lowest energy state before the next phase begins. Even entropy, the relentless driver of decay, could be part of the cycle, rising and falling like breath, rather than racing toward a final stillness. Experimental hints of this idea already exist. In labs, time crystals form under extreme conditions, like chilled quantum systems bombarded with laser pulses. These tiny, man-made structures don't require external energy to keep ticking. They're self-sustaining, driven by quantum coherence. Now imagine a version of this baked into the universe's foundation. Dark energy, the mysterious force accelerating cosmic expansion, might not be a constant after all, but a phase in the cycle. As the universe stretches thin, quantum effects could trigger a reversal, like a coiled spring reaching its limit and rebounding. The result, a new bang, not from nothingness, but from the natural rhythm of space-time itself. Critics argue that scaling up time crystals to universal proportions is speculative at best. Yet the math doesn't forbid it. Some quantum gravity models even suggest that space-time at the smallest scales is granular, with properties resembling a crystalline lattice. If true, then the cosmos might not be smooth and continuous, but more like a cosmic quilt stitched together with threads that vibrate in timeless patterns. The echoes of these vibrations could linger in the cosmic microwave background, or the large-scale structure of galaxies, subtle clues that our universe is just one frame in an infinite film strip. The beauty of this theory isn't just in its audacity, but in its simplicity. A time crystal universe doesn't need extra dimensions or colliding branes to explain rebirth. The mechanism is built in, as fundamental as gravity or light. It suggests that existence isn't a one-act play, but an endless encore, with each iteration varying just enough to keep the story fresh. And if that's true, then every galaxy, every star, every fleeting thought is part of a rhythm older than time itself, a pulse we're only now beginning to hear. Dark matter is the universe's silent architect, an invisible hand shaping galaxies, bending light and holding the cosmos together. But what if its influence runs deeper than we've dared to imagine? Beyond merely sculpting the universe we see, dark matter could be the hidden engine of cosmic rebirth, the unseen force that nudges reality toward renewal. Picture this: as the universe expands and dark matter's gravitational web stretches thin, its subtle interactions might reach a tipping point. Like a slow building pressure in the Earth's crust before an earthquake, dark matter's dynamics could trigger phase transitions, sudden, violent shifts in the fabric of spacetime itself. These aren't just theoretical fireworks, they could be the sparks that ignite new big bangs, birthing fresh universes from the ashes of the old. The mechanics of this process are as elegant as they are mysterious. Most models assume dark matter is inert, interacting only through gravity. But if it has even a faint ability to interact with itself or other forces, through some unknown particle or field, its behavior over cosmic timescales could become unpredictable. Imagine dark matter as a cosmic pendulum, swaying gently for eons until it accumulates enough energy to swing violently, destabilizing the vacuum of space. In brane cosmology, where our universe is a floating membrane in higher dimensional space, dark matter's gravity might be the glue that pulls other branes close enough to collide. Those collisions wouldn't just be cosmic accidents, they'd be inevitabilities orchestrated by dark matter's invisible tug. Evidence for this idea is tantalizingly indirect. Astronomers have noticed dark matter seems to clump in ways that don't always align with predictions, as if it's responding to rules we haven't decoded. Some galaxy clusters show dark matter distributions that defy standard models, hinting at hidden interactions. If these anomalies aren't just measurement errors but glimpses of dark matter's richer physics, then we might be seeing the first clues of its role in cosmic recycling. Even more provocative are theories suggesting dark matter could decay or transform over trillion-year timescales, releasing energy that reshapes the vacuum itself. Like a time bomb set at the dawn of time, dark matter's slow unraveling might one day rewrite the laws of reality. The implications are staggering. If dark matter is the unseen architect of rebirth, then the universe's fate isn't just about visible stars and galaxies, it's about the shadow scaffolding holding them up. A cosmos where dark matter drives cyclical renewal would be self-sustaining, its death and rebirth woven into the same invisible framework. And if we're living in one iteration of that cycle, then dark matter isn't just a mystery to solve, it's the quiet custodian of existence itself, patiently setting the stage for the next act in an endless cosmic drama. Neutron star collisions are among the most violent events in the Cosmos 2 city-sized remnants of dead stars, each more massive than our Sun, smashing together at nearly the speed of light. The energy released in these mergers is so immense that for a split second, they outshine entire galaxies. But beyond the spectacle lies something even more profound. These cataclysmic crashes might be cosmic nurseries, forging conditions so extreme they could birth entirely new universes. Imagine the aftermath of such a collision, a swirling cauldron of quarks, gluons, and exotic matter hotter than the core of a supernova. In that primordial soup, the very fabric of space-time could twist into knots, creating pockets where the laws of physics warp into something unrecognizable. Some theorists propose that within these knots, microscopic bubbles of false vacuum might form, pinching off into self-contained realms with their own unique constants and dimensions. The idea hinges on the strange behavior of matter under such extreme pressures. Neutron stars are already nature's most extreme laboratories, their cores so dense that protons and electrons fuse into neutrons, creating a quantum fluid with properties we barely understand. When two of these stellar corpses collide, the densities and temperatures briefly rival those of the Big Bang itself. In that fleeting moment, the boundary between our universe and something entirely new could blur. Quantum fluctuations, normally too tiny to matter, might suddenly balloon into macroscopic effects, warping space-time into bridges to other realities. It's as if the collision doesn't just scatter debris, it stitches new pockets of existence into the cosmic fabric, like sparks flying from a blacksmith's hammer and igniting hidden tinder. What's staggering is how these cosmic eggs might inherit traits from their parent stars. Just as a child carries genetic markers from their ancestors, a newborn universe spawned in a neutron star collision could bear imprints of the physics that birthed it. The precise ratio of matter to antimatter, the strength of gravity, even the number of spatial dimensions, all might be shaped by the chaotic dance of the colliding stars. Some universes might flicker out instantly, their physics too unstable to sustain structure. Others could flourish, expanding into vast realms where black holes form faster than stars, or where time flows backward in localized pockets. Our own universe, with its delicate balance of forces, might owe its existence to a similar cataclysm in some long-forgotten predecessor. The echoes of this process could be hiding in plain sight. When neutron stars collide, they don't just spew radiation, they also unleash gravitational waves, ripples in space-time that LIGO and other detectors have only recently begun to capture. Hidden in those signals might be subtle anomalies, tiny deviations from Einstein's predictions that hint at space-time buckling into new configurations. Some physicists even speculate that certain fast radio bursts, mysterious blips of energy from distant galaxies, could be the birth cries of nascent universes, their emergence sending shockwaves through our own. Yet the most haunting implication isn't about detection, it's about scale. If neutron star collisions can seed universes, then every such event we've observed wasn't just a stellar death knell, but a cosmic genesis in miniature. The gold in your jewelry, the uranium in reactors, even the calcium in your bones, all were forged in these apocalyptic mergers. Now imagine that same alchemy birthing something infinitely grander, entire realities, each with its own laws, its own history, its own version of this very question. The night sky isn't just a graveyard of dead stars. It's a constellation of cosmic wombs, each one a reminder that even in destruction, the universe keeps planting seeds for tomorrow. What if the death of our universe isn't an ending at all, but a transformation? A cosmic caterpillar dissolving into higher dimensional soup before emerging as something entirely new. The idea of extra dimensions isn't just science fiction. String theory and M-theory propose that reality might have 10 or even 11 dimensions, most of them curled up so tightly we'd never notice. But in the universe's final moments, as entropy maxes out and spacetime stretches thin, those hidden dimensions could unfurl like a flower blooming in reverse. Picture our four-dimensional spacetime, length, width, height, and time slowly peeling back to reveal a grander architecture, a fifth dimension where the old rules no longer apply. In this higher dimensional realm, the energy and information of our dying universe might not vanish. It could simply migrate, reshuffling into the blueprint of a fresh cosmos. This isn't just poetic speculation, it's grounded in the math of brane cosmology. Imagine our universe as a three-dimensional sheet floating in a higher dimensional bulk. When our brain grows cold and lifeless, the higher dimensional environment could still thrum with activity. Quantum fluctuations or gravitational instabilities might trigger a new brain to bud off, like a soap bubble splitting in midair. This newborn universe wouldn't erupt from nothingness. It would inherit energy and structure from the higher dimensional scaffolding, making the Big Bang less of a beginning and more of a phase transition. Think of it like folding a piece of paper into an origami swan. The paper's essence remains, but its form transforms into something unrecognizable. The implications are dizzying. If higher dimensions exist, then the heat death of our universe, the cold, lifeless equilibrium we fear, might just be a local phenomenon. While our pocket of reality fades, other dimensions could remain vibrant, hosting processes we can't fathom. Some theories even suggest that the gravitational pull we attribute to dark matter is actually the tug of parallel branes in these extra dimensions. If that's true, then the very force holding galaxies together could be the same force that eventually stitches a new cosmos from the old one's remnants. But how would this multidimensional rebirth actually unfold? One possibility involves quantum tunneling on a cosmic scale. As our universe decays, it might not collapse into oblivion but tunnel through the higher dimensional landscape, emerging in a fresh configuration with reset entropy. It's as if the universe rolls downhill into a valley of stability, only to find a hidden tunnel leading back to the mountaintop. Another idea posits that black holes, those cosmic shredders, could be gateways. When a black hole's singularity reaches Planck-scale densities, it might puncture our brain, spewing its contents into the bulk where they seed a new spacetime bubble. The beauty of this theory lies in its defiance of linear thinking. In 4 dimensions, death seems final, but in 5 or 6 or 11, endings might just be bends in a geometry we're too limited to perceive. If true, then every galaxy, every atom, every fleeting thought is part of a story too vast to be contained by a single universe's lifespan. And somewhere in the dark, beyond the edges of our perception, dimensions we can't imagine might already be weaving the next chapter. From the fiery collapse of the Big Crunch to the abstract rebirth of holographic data, these 29 theories paint a stunning picture of a universe that refuses to die. Whether through brane collisions, quantum resurrections, or simulated reboots, the cosmos might have endless tricks to cheat oblivion. As we peer deeper into these mysteries, we're reminded that the universe's story is far from over. It might just be on an eternal loop. Consider the sheer audacity of these ideas: black holes birthing universes, time folding back on itself like an infinite Möbius strip, or reality itself being a holographic projection from some distant cosmic boundary. Each theory challenges our most basic assumptions about beginnings and endings, turning what we thought were finales into intermissions. The universe, it seems, has a flair for reinvention. Even in its darkest hour, when stars fade and black holes evaporate, the potential for rebirth lingers like a whisper in the void. What's truly humbling is how these theories bridge ancient wisdom and cutting-edge science. Hindu cosmology spoke of endless cycles of creation and destruction, while modern physicists scribble equations for bouncing universes and colliding branes. The details change, but the theme remains: existence is resilient. Whether through the slow decay of entropy or the violent spark of a singularity, the cosmos finds a way to continue. And if even one of these theories holds a grain of truth, then the night sky isn't just a collection of distant lights, it's a glimpse into an infinite story, where every ending is just a prelude to another beginning. So where does that leave us as tiny observers on a pale blue dot? We're left to marvel at the scale of these possibilities. The universe might be older than we can fathom, with past lives etched into the fabric of spacetime itself. Or perhaps we're living in the first act of a grand cosmic drama with countless iterations yet to come. Either way, one thing is certain: the universe is far stranger, far more inventive than we ever imagined. If you're as fascinated by cosmic rebirth as we are, hit like, subscribe, and let us know in the comments which theory blew your mind the most. Was it the holographic universe's data-driven resurrection, the eerie elegance of Penrose's conformal cycles, or the spine-tingling possibility that we're all living in a simulation waiting to reboot? Whatever your pick, one thing's for sure: the cosmos has never been more mysterious or more alive with